Now, the next speaker is Avi Wigderson. Avi Wigderson, let me just give you very briefly some information about him. He was, I assume, born in Israel. He was certainly educated in Israel at the Technion Institute of Technology. His doctorate degree he took here in the computer science department at Princeton University. And he was for 12 years at the Hebrew University in Jerusalem in the Computer Science Institute. He came to here in 1999. And I'll just mention one prize. He received in 1994 the Neven-Lina Prize, which, as you may know, is a prize given every 4 years to a theoretical computer scientist. Very few have been given. All of the recipients have been very distinguished. He has a great deal of responsibility, of course, for computer science, theoretical computer science, here at the Institute, and also for combinatorics. He's not alone in some sense. Alexander Razbov has been here for several years. He's not here permanently. He's also a recipient of the Neven-Lina Prize, so I assume it's quite a good aid. And Noga Alon is also here frequently from Jerusalem, and he also, I assume, does a good deal, but nonetheless it's an extremely lively program in computer science, as you see. A lot of people and a lot of activities. However, Avi Wigderson is alone in representing theoretical computer science on the faculty, so he has a difficult task. He has to defend the interests of computer science, and that he's helped in that by his passionate affection for the subject itself, by his wide knowledge for the subject itself, and his persuasive abilities. This doesn't mean that he doesn't have a sympathetic audience, that we're not trying our best to be convinced, but nonetheless he does a magnificent job, and I think he'll display all those qualities during today's lecture.
Thank you very much. Everybody hears me? I guess I don't have a loud voice like Peter. I'm going to be also less ambitious than Peter. I'll talk just about two permanent faculty of the Institute, those who have done theoretical computer science here before me, or even before the field was a field. Kurt Gödel and John von Neumann. 2 comments about von Neumann. It seems that everybody called him Johnny, and I'll stick to that. And I'm not going to talk about the computer, which von Neumann built here. I'm sure that George Dyson will tell you about that. I want to talk about the mathematical ideas of von Neumann and of Kurt Gödel and their relation to my field of study, which is the theory of computation, to computation. Now, of course, they were mathematicians. They did mathematics much in the style that you saw in Peter Sarnak's talk, but I want to talk about the concepts that they studied. And these concepts are actually related to everybody. They are fundamental concepts. Let's see if this works. Very interesting. Oh, what about this? Okay, good. It works. So I want to talk about these fundamental concepts, and actually there will be quite a few of them. That's more or less the plan of the talk, talking about these things. I'll talk about truth. I'll talk about proof. I'll talk about computation, which will come up again and again throughout the talk, and its limits. I'll talk about efficient computation, which is the main activity of theoretical computer scientists today, understanding what can be done and how it originates in some sense in Gödel. I'll talk about higher issues. It could be a Dyson talk about life and intelligence, von Neumann cellular automata. I'll talk about more down-to-earth issues of fault tolerance, but in very general situations, to noise, to errors, to infections, and you'll see how it comes up in relation to computation and to objects. I'll talk about expander graphs. Randomness is one one concept that humanity grappled with, I think, for millennia, and we still don't understand it, but we understand it much better, starting with some work of von Neumann and a lot of work that's being done today in my field. And I'll talk about games if I get to it. So we have a long program, so let me start. When I said that we'll talk about truth, we want to know the truth about some statements, and in mathematics it's about mathematical statements, like you've seen before. So let me give you examples of some mathematical statements. You've seen some in Peter's talk. Here's a statement: x plus y times x minus y equals x squared minus y squared. Okay. Here's another more interesting one. There are infinitely many primes. Here's another one, the statement of Fermat's last theorem, so-called. Here's another statement: every even number is the sum of 2 squares. You'd like to know whether this statement, 2 primes, thank you. You confused me. I actually listened to you. We want to know if they are true. So, they are not obviously, each of them is about infinitely many things. If you want to check, you need to check infinitely many things. But the nice thing about mathematics, which makes it different than all other subjects of study, is that we can know absolute truth because we have proofs. We have proofs that if we can manage to prove any one of these statements, we know it's absolutely true. So let me talk about that. First, let's see what is the proof. So, proofs you saw in, again, I'll refer to Peter's talk. It was a great example. Proofs are or can be complicated, but their structure, their essence is very simple. I want to talk about that because it will be important. So, what is a proof? A proof has two ingredients. Axioms, these are the things you start with. These are the self-evident truths, like 0 plus 1 is 1. Or if you're in geometry, between any 2 points, there is exactly one straight line. These are the self-evident facts. And then you have deduction rules, which enable you to deduce new true facts from old ones that you know are already true. And these deduction rules have to be simple and local. They are applied, let's say, in this case, to if you know that A is true, you know that B is true, then you can infer that the conjunction A and B is also a true mathematical statement. And once you have this, what is the proof of some particular statement T? Well, it's just a sequence. In the beginning of the sequence, you lay down some of the axioms you have, and then you keep deducing new and new statements using an application of a deduction rule to, let's say, to two previous statements you already proved. And if the last element of the sequence is T, then you have proved T. Okay, that's the proof. It's a very simple, has a very simple structure. And as I said, the truth of axioms implied, and of course the soundness of these deduction rules implies the truth of T. Now, while generating a proof may require amazing creativity, the verification of proof, just because of this structure, is a very simple mechanical process. And that's very important. So this is the proof, and if we have it, then we also have truth. So let's see about the statements we talked about. Well, the first one is sort of trivial middle school thing, so everyone can do it. The second was done by Euclid about 2,400 years ago, and Euclid is the father of proofs as we understand them today, of the logical deduction. And that's already, it's an ingenious proof, but very simple. The third statement was mentioned before. This is the wild, remarkable result that took 300 years to resolve. So here's a proof that took a long time to come by, but we did come by it. And the fourth statement, well, actually, we don't know. And this is called the Goldbach conjecture. And the main question, well, it's either true or false, right? So can we prove it? Will we ever know, at least potentially, will we ever know the truth of that via a proof? So it's a fundamental question that is underlying every mathematician's work, that what they are trying to prove, in fact, maybe they will not get it, but it is there somewhere. So that's the question, that's the fundamental question. Is there a complete proof system that proves every true statement? And it was a shock to the mathematics community when Gödel proved his incompleteness theorem, the fundamental fact that the world is not perfect. We have to accept the fact that no matter what proof system we use, there will be some true statements that we will never be able to prove. By the way, this was his PhD thesis, so part of his PhD thesis. Let me switch to computation, and you'll see immediately the analogy and why I talked about proof. Well, again, computation can be very complex, and I'm sure none of you, like me, understand what's going on in the hearts of your PCs. But the idea, the structure is very simple. There are two major building blocks to computation. One is the input, it's the data you are starting with. And second is basic operations, very simple operations like addition or conjunction or whatever, simple operations, local, simple and local, like before. And a computation of some function, let's say f, is you start with the data you are given, x1 to xk, and then you start computing new values by applying these local operations to previously computed values till you get the function at this function value at this input. So, as before, it's exactly the same structure of a proof, except that we demand that this sequence be generated for any input via a finite deterministic program. So unlike before, proof, it exists, maybe it takes a genius to find it. Here, computation, we specify, write a program that will compute f for us. Okay, so we have this. So what's the connection between these two? Well, there are lots of connections. Actually, throughout history, in fact, Peter was mentioning, these people, all the, Gauss and Euler and Ramanujan and everybody he mentioned, actually, when they tried to prove things, they actually did some computation. They computed examples, and there is a connection between computation and proof going hand in hand through history. But it was made formal only in the beginning of this century, and all fathers of this theory of computation that I'm part of is, were logicians. Church, Kleene, Post, Turing, Gödel, definitely. And what did they do for this theory? Well, what they did is they developed formal models of computation, and actually different ones. The winner model was, I think many of you know, is the Turing machine, which is the theoretical mother of all computers, and in particular of von Neumann's computer. And even though the models were different, they're trying to understand what computation is. They quickly realized that all these models, even though they looked very different, are actually did the same and computed the same things. And they definitely all share this feature. You are not allowed to gestalt in computation. You have to do simple local operations. So in some sense, this is also a talk about from local to global. You do very local operations. You want to compute something very complex. And they came up with this thesis, which sounds very bold, very amazing. They say, well, our model, actually, the Turing machine, can do anything that any other computer can do, whatever you make it, from gases, from, I don't know, quantum effects. This is everything that can be computed. We'll go back to that, but once we have we think we understand what a computer is, theoretically, it's a basic question again, like the question we asked before about proof and truth. Here's the question is, which functions can be computed? Can computers do everything? It's a very basic question. And the person to answer this was Turing, is the famous undecidability theorem. This, by the way, was his PhD thesis. There are functions which cannot be computed. Computers are not all powerful. So that's the first fundamental fact about computation. And actually, let me prove this to you. Assuming Gödel's incompleteness theorem. Okay? Here's the proof. Let's look at this particular function. This function takes a mathematical statement and says 1 if it's true and 0 if it's false. It's a function, well defined. And we compute it. Well, it's very easy to see. I mean, it's really easy to see that a program for F will constitute a complete proof system and therefore violate Gödel's result. So here's the proof. Actually, it's not the way Turing proved his result. He actually did it in a much simpler way, and actually in a way that infers Gödel's result, but let me not talk about that. So we know something fundamental about computation. But in fact, I mean, once these fundamental facts were known, it was clear very fast. Became clear that what we really want to understand is not computation in principle, but efficient computation. Computation we can do in our lifetime. Computation, if we would like the computer that computes our salary checks to actually finish, by the end of the month rather than by the end of the decade. So we have to understand which computational problems can be solved quickly and which cannot. And actually, let me give you an example of a function that is in principle computable, it's obvious, but whose efficiency is crucial certainly to the School of Mathematics and all mathematicians everywhere, which is this function, okay? It's a slight variation on the previous function. Here, the arguments to the functions are a mathematical statement T and a number n, and we want to know whether this statement T has a proof of length n, okay? Suddenly, when we start trying to prove something, we know that we expect that it will have a proof of at most 50 or 100 pages. Otherwise, we wouldn't, we have no hope, right? Well, some finite amount. So we all know implicitly an upper bound on the length of the proof when we try to solve something. So how hard is this function? Well, here, let me show you that it's computable. It's very simple. A monkey can do it. Okay, so what is the monkey solution? We just write down all sequences of length n, all books of 100 pages. And since to verify if something is a proof is a simple mechanical process, we verify, then we are done. So it's computable, but of course, it's not efficient. It's terribly inefficient. The time to run this process is 2 to the n, which with even moderate n is something that, and with the fastest computers, 1 in every atom of the universe running at the speed of light will not finish. Okay, so this is terrible. So what is the complexity? I mean, of course, let me show you. Gödel's that. I mean, we are interested in that. We have developed the theory of computational complexity to try to understand and even define this question, what is efficient, what is not, in the last 30 years. But actually, recently it was discovered that Gödel wrote to von Neumann a letter in which he basically understood completely what it was about. He asked, is there an efficient algorithm for this function? And he defined efficient. He said it is possible that this is as a solution in n or n squared steps. And it's clearly understood that, I mean, if this is, if this is true, we can replace the whole school of mathematics, not only here, but in all the universities in the world, by, little PCs. This is the essence of the P versus NP question, which, like the Riemann hypothesis, the Clay Mathematics Institute offers $1 million for, and like the Riemann hypothesis, if that's your motivation, you better work on something else. The difference between the problems is that this problem, evidently, by the way I described it, asks about our ability or the ability of a simple computer program to solve the Riemann hypothesis. And as I said, it's a major problem, in fact, of computation complexity and of mathematics. And the reason it's so fundamental, it actually goes beyond mathematics. It captures in a very fundamental way the question of whether creativity, which we somehow associate with the proof of mathematical theorem, can it be automated? Can it be efficiently automated? Okay. Let's go up. Douglas Adams' books, the life, the universe, and everything. This is a kind of issue we want to tackle now. I mean, what is really computation? I mean, we define it in the most general way, and actually, certainly not. Let me go back to what I mentioned was a Church-Turing thesis. It's a very bold thesis, of course, which cannot be proved. It's just a belief that a Turing machine or this laptop captures everything that can be computable. There's nothing, no way, no physical way to compute more than what this laptop can do, no matter what you use. And to sort of study this, we should look what would be called computation in general. And from these examples I've given, we want to make one thing sure. There's no gestalt is allowed. You can do what you want as long as the rules you apply are local and simple. Okay? And now we can look around in the world around us and look for computation. And actually, everywhere, almost all physics and biology theories satisfy this kind of, local and simple application of rules. And, everywhere you look, and, I just ran out of space, you see examples of computation. I mean, in physics, in magnets, in the weather, in nuclear fission, in burning fire, you see the evolution is of this form. And in the, in ecology, in ant colonies, or in schools of fish or other populations, you see the same. In our bodies, you see the same. In the brain, in epidemics, in proteins in the cell, regeneration. I broke my toe in a basketball match a couple of months ago, and I broke a nail of my toe, and now my toe is computing a new nail. So it works. Actually, very locally and very slowly. There's one difference between all these examples and the Turing machine, in that things happen. These local simple rules are applied at the same time in many places. So in some sense, it's a slightly different type of computation. And in fact, von Neumann studied this model of computation. He called it cellular automata. And let me describe to you this model. This model has a collection of cells, very large, maybe infinite collection of cells. In this case, it's the plane lattice. It has a neighborhood structure. You have to decide for each cell who are its neighbors. For example, here we can decide it's just itself and all the other cells that touch it. Okay. It has a finite state space, so every cell can be in one of a few states, which I do in colors here, for example, green or yellow. And then it has an update rule. What will I be next? Okay, so it's a simple rule. You look at your neighborhood and decide what you want to be next. And here we'll pick the example that it will be the majority vote. It will be what the majority of your neighborhood is right now. And finally, there is what we start from, the initial configuration like this one. So let's see, for example, here what will we expect to happen in the next step to this cell, where we have to look at its neighborhood. And, well, all the neighborhood is green. It will remain green. Let's look at another guy, this guy. So here, 6 out of 9 are green. It will also remain green in the next step. Let's look at another guy. This guy. It is green now, but 5 of its neighborhood is yellow, so it will switch to yellow. In fact, you can see that all the yellow guys will remain yellow. Okay, so let's just do an example. Yeah, he will turn to yellow. So let's look at an example. This example, now it all happens in parallel. So in the first step, all corners will disappear, right? will become yellow, and then these 4 will disappear, and finally, the 3 steps, it will be all green. So that's an example of an evolution of a cellular automaton. Let me just remark, because we'll need it later, you can associate whatever meaning you want to these colors or states. And in fact, if this is a model of some physical or biological phenomena, there would be meaning. And if green, for example, was infection, then actually you can study whether it will die out. And in fact, it will be interesting to also ask how fast will it die out. So we'll go back to this. But let's go back to these higher issues. Well, this model is great for understanding dynamics in biology, physics, ecology, systems like that. And you can look for, and people do tons and tons of simulations on this. You can look for emergence of patterns, maybe chaos, but you can really seriously try to understand whether, they capture some essence of really important, philosophically important subjects like life and intelligence. And indeed, the reason von Neumann studied them was to understand a particular aspect that we usually associate with life, namely the self-replication. Okay? That's what he wanted to understand. So what he was trying to build is something of this type, maybe with a different rule or a different neighborhood structure, in which you can put a pattern there, and after some finite number of iterations, it will give birth to another guy like him. And then this will, or more, maybe it will have a few kids, and so on and so forth. That's what he was saying. He asked whether this can be done with finite, with a simple local operation. And in fact, he succeeded. He succeeded. It's a great achievement. I think the rule that he needed was quite complicated. So it was simple and local, but, with big numbers. And the best, solution to this problem, and actually, as you see, to other problems, is the Conway's game of life. Conway's game of life is another cellular automaton. Actually, it has the same structure like before. It's on the plain lattice, and just 2 colors. And the rule is slightly different, but it's like a majority vote. It's just, some kind of weighted majority vote. So it's a very, very simple rule. Bacteria could simulate it. Okay, it just. And it turns out that there are patterns in Conway's game of life. You can go to the web, you can find lots of demonstrations, which can reproduce themselves. And you can ask them yourself, do you think that this, there is life there in this artificial game? I said that bacteria could simulate, or ants definitely could simulate this Conway rule. So when do we say that, a species is intelligent? Usually we look at what they do, and if we see some behavior patterns that are, we see bees communicating, or we see ants, do communal effort, we associate somehow intelligence to that. Suppose these ants actually started listing down the prime numbers. Will you say they are intelligent or not? It's a serious question. Well, it turns out that Conway's model can do it, so ants can do it. And actually, there are other things. If you just give you a pattern and ask in Conway's game, will it go forever or stop somewhere? This is an incomputable function. And there are more and more I can say, but actually, you should guess why this is. It's because Conway's game of life is a universal Turing machine. It's a universal computer. So that explains it. Okay. Talked about cellular automata. Let me talk about totally different problem, which you'll see is, again, related somehow, all in von Neumann's amazing brain. So von Neumann needed to build his computer. I have to mention it, but I want to talk about some ideas. And one of his major problems was that the hardware of the time was terribly unreliable. But he wanted to, carry out long computations with these unreliable gates or elements, computing elements. And like everything else he did, he built a model and tried to understand what to do with it theoretically. So we look at some small piece of a huge computation. This is just one gate. It gets 2 inputs and has 1 output, local, simple. And this gate may create errors sometimes. Okay, so let's denote by yellow a correct value and green incorrect value. And suppose that 2 inputs are somehow arrived from the previous computation intact. They are correct. The model is that on correct inputs, with some small probability, the gate will produce an incorrect answer. Let's say with 1% probability, it will produce a wrong answer. Okay. Now, if this happened only here, it would be no problem. But the computation is big. It happens again and again and again, and it just devastates, ruins the computation completely. So what do you do? There is an idea, which von Neumann had, replicate. Just have many copies of each value you want to compute, and then you might hope that a few of them will be wrong, but maybe the majority will be good. Okay? Of course, as is, it just doesn't work. It suffers from the same basic problem. Why? Because maybe this came with an error before, and this error propagates to the output. If we have an error in the input, we cannot know what will happen. The output cannot assume it will correct itself somehow. And similarly, from the right, there was some error which propagates. And on top of this, the gate created another error. So again, it will accumulate and destroy the computation. So here was von Neumann's insight. He said, why don't we alternate? One step, we perform a gate like this on all these copies, and the other, we perform some cleanup, some error reduction via the cellular automata idea, via some, let's say, majority vote over some neighborhood. This will reduce the errors, like we saw with the infection before. That's why I kept these colors. Well, this idea is not so simple to, it's not clear that it works because there is a competition here. On the one hand, the majority, local majority somehow, at least intuitively, you would believe, reduces the errors. But how do you do this majority? Also with your unreliable elements, so they create errors. So somehow you have to reduce error faster than they are created. So what do you have to understand? What you have to understand is which structure, which neighborhood structure is best for this purpose. Okay, so you can arrange these copies in many patterns. You can arrange them on the lattice, and then actually the decay of errors is not so fast. You can arrange them maybe on a cycle. So neighborhoods for me are those connected with these line bars, which are called edges, and this object is called a graph. So it's clear what a neighborhood is. You can build this kind of a graph or this kind of a graph, like put them on the corners of a cube, or you can do what you like. It just has to be a sparse graph, a graph with not too many edges, because again, computation is local, has to be local. So on which graph does infection, die fastest? It's a basic question. We might also want to study whether within our bodies, the way antibodies are fighting viruses is what structure we are using and so on. But anyway, if you think about it, it turns out that you come to a question about fault-tolerant computing, which is totally different than the previous one. It came from the other one, but it's totally new. It's the question that you want to construct a graph with very few edges, just everyone has very few neighbors, a graph in which is very highly connected. Somehow, in order to disconnect a large part from it, you have to sever many edges. You have to, so it's fault tolerant in a different sense, in actually a sense that's very fundamental to network theory. And these kind of graphs are called expander graphs. Now, von Neumann needed such graphs, and actually he couldn't construct them, but he had, again, a beautiful insight. He said, let's just draw them randomly. Let's connect everyone to 3 random neighbors, and let's do the majority vote on this. And actually it works. It's really good. But somehow it's not completely satisfactory because we don't really understand when we get this random graph, that, random, behaves, as it should probably most of the time, but does it always, and so on, and is it the best? So the question of explicitly constructing such graphs has been a major problem, and we are still studying it, but for about 30 years, and where would you find them? Well, actually, you should go to the people you suspect least of working on these problems, like Selberg and Delin. This connection to number theory was made by Alex Lubotsky, Peter Sarnak, and Phillips. What's his first name? I forget. Yeah, about 20 years or 15 years ago, and also by Margulis. It turned out that the place to look for these remarkable objects is in number theory. You go to Selberg's work on the spectrum of congruent subgroups of the modular group, and you get a pretty good expander. And actually, you go to Delin's work, which Peter mentioned on solving the Ramanujan conjecture for algebraic varieties, and you get the optimal expanders, at least in some sense of optimal. So this is quite remarkable. Okay, time to switch gears again. This time you can wake up again, forget what I'm sure you forgot already, but okay. I want to talk about randomness, and again, there's I could devote, well, to each one of the subjects I could devote a long lecture or a long course. Randomness is a particularly rich field of study then and now, and let me tell you about some of its origins in the way that we know them today. And again, starting with Johnny and his friends, well, starting with the bomb, people were very interested at the time to understand neutron diffusion, and Stan Ulam and von Neumann and Metropolis and other guys in Los Alamos, who helped in Los Alamos, came out with this wonderful idea, which they call the Monte Carlo method, which is, you know, you should think of gambling or randomness coming in. That's the source of the problem. They said computation should not be restricted to being deterministic. We can flip coins. Maybe we can use those coin flips to enhance computation, to do it better, faster, more efficient. Now, it's not like they invented the idea, because statisticians have been using it before, but I would say that from the time of the Monte Carlo method, the topic, the subject, this huge field of probabilistic algorithms became rich, because people started to do non-trivial things in non-trivial algorithms using randomization. And this field has been extremely successful, and we understand today, we know probabilistic algorithms for a variety of problems in statistical physics, algebra, geometry, group theory, optimization in industry, and lots of scientific and other sciences. Probabilistic algorithms that are much more efficient than their deterministic counterparts. They are just, you know, at least as far as we know, there are no deterministic matches to this performance of these probabilistic algorithms. So we come again to a fundamental question. Is it true or is it an illusion, this amazing power of randomness? Can randomness really speed up computation, or simply we were not clever enough yet to generate the deterministic algorithms that achieve the same performance? It's a basic question that we are still grappling with. We don't understand. We don't know the answer to it. But let me tell you something remarkable that we've been able to do in the last couple of decades in attempt to understand it, or the last decade. While we cannot answer this question, we can relate it to another open question that I already mentioned, to the P versus NP problem. So somehow we know that there is no speed up if P is different than NP. So let me say it slowly so you'll see what's going on here. I mean, you won't see what's going on, but maybe you'll be amazed. So it turns out that if P is, I put quotes here because there's more technical statement, and like Peter, I'm cheating you right and left everywhere. But basically, if P is different than NP, as we expect, if creativity cannot be automated, then this amazing power of randomness is actually fiction. We can replace each and every one of these probabilistic algorithms by a deterministic algorithm that does essentially as well. What's the connection? Where is it coming from? Well, I'll tell you a little bit about it. So when von Neumann was studying these probabilistic algorithms, these Monte Carlo algorithms, he asked the obvious question that everybody asks, and everybody who is first facing this idea of probabilistic algorithm. Well, where do you take these coin tosses? Well, are you standing next to the computer and toss them? Well, where are they coming from? And I mean, the answer depends. There are two answers, two obvious answers at least. It depends on whether you think the universe is deterministic or not. And if you think it is, then you can try to generate these random numbers deterministically. Of course, the analysis depends on them being independent, but you can feed it what you like and hope for the best. So these gadgets which create these, deterministically create these sequences are called pseudo-random generators, and von Neumann studied them and made some initial, not real theorems, but some really important observations. By the way, he made this immortal saying, anyone who's trying to generate random numbers by deterministic means is, of course, living in a state of sin. But even though he said it, he was trying to make sense of what, is it really sin? And to really understand what's going on, we have to understand what is randomness for the setting we are studying, for its use in probabilistic algorithms, in efficient computation. And that's something that we've been doing, trying to come up with definitions which captures exactly what is needed from the pseudo-random generators. And here is the source or the germ of the idea that actually functions which are hard to compute. So if you know that something is hard to compute, usually it's bad news. You just wanted to compute it and you can't. So that's really bad news. But actually, in the setting of pseudo-random generation, that's good news. If you have a function that's hard to compute, if P is different than NP, then you can use it to build good pseudo-random generators and replace randomness by determinism. That's very, very quickly the source of the theorem I showed you before. Now, if you believe that there is, randomness in nature, you can tap to it, right? So you can go to whatever your favorite noise model, radioactive decay or the weather, or weather prediction for that matter. You can look at stock market fluctuations. You can look at internet traffic. There are all sorts of sources of noise in this world, and you can, things that look random, and you can just try to use them in your algorithms instead of these perfect points. But it's clear that all these sources of randomness are weak in some sense. I mean, maybe they contain some entropy, some randomness, but certainly it's not like pure conflicts. There are biases, there are dependencies, and so on. So this is another big field. So I said pseudo-randomness is one big field, and another big field is this field of weak random sources and randomness extraction. You are trying to understand, suppose I give you such a weak source, a source which has some entropy, but you don't know where it is, you don't know what the correlations are, you just know that there is some entropy there. Can you purify it? Can you extract the entropy out in perfect form, in a form of perfect coin flips? And that's, again, a beautiful and very rich subject. Again, von Neumann did some preliminary work on it, and it was taken to, well, I cannot, let me stop here about this. It's a great field, and again, still active. And I'll make my last switch of the day, and I'll be very brief. Well, I guess I'm perfectly on time. So tell you just a little bit on the tip of a fork on von Neumann game theory. In 1928, von Neumann proved the minimax theorem. It's not his thesis, it was like a couple of years after he submitted his PhD thesis, so it ruins a little bit my story. But anyway, this was the first step in a major work that he carried out with Oscar Morgenstern here in Princeton, game theory. And they have published this book, which I believe you've heard of, The Theory of Games and Economic Behavior. And I would say that this is one piece of mathematics that has been extremely important to society. What they did for the first time is to make conflicts everywhere in economics, politics, war, law, and everyday life amenable to mathematical analysis. They set it on formal foundations and provided tools to actually understand what we should do in conflict situations. The basic question of game theory is the following. I mean, given a conflict, and the interesting conflicts are the conflicts we know in life, these conflicts in which it is your decision and the decisions of the other participants that together affect the outcome. And you can start thinking, will I do, what if he knows that I'll do, and so on. Just going to which strategy you should choose that will achieve the best. And before this work, people treated it like, well, sometimes what you do, maybe, you throw your hands in the air, you behave according to your character or your impulse or, what you feel like. But actually, it turns out that you are interested in many ways you can answer the question of whether there is a rational solution. There is a solution that is based on mathematical grounds. And again, as I said, the first solution was in the restricted case of two-person zero-sum games. These are games in which the interests of the two players are completely opposite to each other. And von Neumann gave a complete solution, answering, yes, there is a rational solution. This was generalized in a vast way by John Nash in 1950 to any number of people and interests which can be overlapping or opposing, whatever, using the notion of Nash equilibrium, for which he got the Nobel Prize a few years ago. Let me just say a few words on the minimax theorem, which I now mentioned is a special case of what Nash did, but nevertheless, it's of extreme importance even today. Turns out, first of all, that it is equivalent to the duality theorem for linear programming. Linear programming is a very important mathematical problem that comes up a lot in optimization, and in fact, a lot is an understatement. I cannot imagine of any company in the world that has something to optimize that's not using linear programming. It's very important theoretically. We analyze actually probabilistic algorithms using the minimax theorem and more and more. Finally, what does it have to do directly with the computation? Well, it turns out that there is a new field now alive for about 10 years, which is called algorithmic game theory, in which people are studying is sort of on the boundary of theoretical computer science and of game theory, in which the object of study is sort of rational Turing machines. These are interacting computers that, on the one hand, are bounded by the usual restrictions of computation. They have to be efficient. They cannot do everything, and so on. And on the other hand, they have interests. One of the reasons that it emerged about 10 years ago is the internet. Actually, the internet is the most remarkable thing if you think about it, because no company or no government created it. It sort of grew spontaneously by individuals, companies that had each and every one who participates in this internet consortium had their own interests, and nevertheless you see them do lots of altruistic things. I mean, they keep routing other people's messages. They are doing services to others that nobody requested them to do and nobody is paying them to do, but they still do it, and you want to understand why. And you actually want to understand also how to actually impose or add, incentives in a way that will make it even better. I mean, you'll all agree it's remarkably efficient, right? Even though there's no superpower involved in creating it. So this is some of the topics studied in algorithmic game theory. Now, I think you'll find it hard to believe, but I didn't tell you everything. Thank you.
Well, I think you can appreciate now how infectious the enthusiasm is with which Avi speaks about his subject, and I suspect you have questions. This one. Repeat the question.
Of what? Axiom of choice, yeah. Okay, so let me summarize the question. The question was, I of course oversimplified when I described the notion of probability and truth. And the question was about whether some things should be taken as axioms or as deduction rules, whatever you want to think about, and are they self-evident enough? And the question mentioned the axiom of choice. This is, I'll not explain it, but it's a tool that is used in some proofs, but somehow people preferred. I don't think it's the case today, but 50 years ago, people were very hesitant to use it as proofs, in proofs. And one of so the question was whether there are models in which or theories you can assume it's false. Okay, so it's sort of independent of our current axioms. But the question is it okay to use it if we are not somehow sure? It doesn't follow from the usual axioms, for example, of set theory. So I think a good answer to a more general question is that mathematicians who do number theory or do any other kind of mathematics today are not really worried because of Gödel's incompleteness theorem. They are not worried because they feel that whatever they need is they believe there is a proof within the framework they are working on. Sometimes you come into and this doesn't happen too often, to a question of a fundamental construct like the axiom of choice, which is not obvious whether you should be allowed to use it or not. In fact, it took a lot of work, Gödel's work, to prove that the axiom of choice was consistent with set theory. So it at least doesn't contradict the axioms of set theory, but once it's consistent, people feel comfortable today with using it. There are lots of work that has to do with the infinite or with the higher than infinite, can have this kind of controversies, but for most down-to-earth mathematics, it doesn't exist. Okay. What do computer scientists do? I'm sure I recommend theoretical computer scientists do with respect to artificial intelligence. I think that actually, those of you who are here could not be at the same time at the computer science department in Princeton University where Leslie Valiant was giving a talk just exactly from 4 to 5 like me. Leslie Valiant is a theoretical computer scientist and the father of what is called computational learning theory. Learning theory deals with situations where we have to make, we are given some data in some, from whatever source, language or biological or astronomical or whatever. We have to make sense out of it. This is a basic scientific question. Okay. Now it's also the question that you would like your robots to be able to solve. You put them on some terrain, on Mars or wherever, and you want them to, of course, you teach them a lot, what you know or what you expect, but they face problems that they've not seen before, and they're supposed to deal with this, with the data they acquire. They have to throw away the garbage and retain the essence in some sense. So theoretical computer science has come up with a good model, or actually several models of this notion of learning in a computational setting where they actually, the machines are restricted by their computational abilities, and tries to discern the border between what is learnable and what is not. And that's a very important part of artificial intelligence. You can think of what Google does as, or lots of what is searches that are getting more and more sophisticated can be made tailor-made as some kind of artificial intelligence. I think that somehow the 60s created a hype about artificial intelligence that gave these two words a very bad name. Artificial intelligence, there was a hype like we'll have a computer behaving like people in all possible ways within 10 years. This, of course, crashed. But since in the 80s, again, it picked up, I think there was renewed investment in artificial intelligence in much more restricted and well understood directions in the visual system, in the other cognitive things we can do that we want to teach a computer to do. It's much more focused, and it's clear that it will take a long way, but theoretical computer science is involved with it in a very important way, I think. There are two, yeah? Yeah, go ahead. Well, it's also simple to answer. When you look at things I didn't make any universal claim, but the idea is that if you look at things at the right scale, an element, whatever it is, a cell in the body or a fish in a school of fish or the weather in a particular cubic centimeter, updates its value from its neighborhood by a simple rule. Now, it's automatically simple. If you assume that the state of the cell is finite, it has 10 possible values, its temperature, or it's, whether it's white or black, or alive or dead, and it looks at, 9 or 100 other such elements and compute a function of all of these. This function is simple by definition because there are a few values, just the truth table of such a function is small. And in fact, in life, it's even simpler than that. It's not, most of these phenomena, when you look at them at the right scale, it seems that the rules are simple. I would ask you to give me an example of something which has a really complicated, something that just cannot be described. I think, again, like when we mathematicians study theorems, we expect that they will be solved. When biologists study various systems, they expect that there is a simple explanation theory, and it's simple in the sense. Buzz, you want to ask? Yeah. It applies, what I said applies to this problem. Sorry, very good. Yeah, so I'll let you finish. No. There is no proven difference. Let me repeat the question. So the question was the following. What was said is that for a particular problem, this is a problem, a very important mathematical problem. I give you a convex body. What is its volume? Can you say it exactly or even approximately? It stated that there is a theorem saying that probabilistically you can do it fast, and deterministically you simply cannot do it fast. And so somehow something is wrong with the theorem. But actually something is wrong with the theorem you mentioned. And what's wrong with it is that it works in a particular abstract model of computation. It does not natural. Let me ask you that. But it's in an extremely restricted model of computation, this result. It does not apply to Turing machine it does not apply to my PC. Okay? So the fact that I'll be able to run a deterministic algorithm on my PC to solve this problem deterministically would not violate the problem you mentioned, because this model is extremely restricted. It's so restricted that all it allows you to do is to answer questions whether a point is inside the body or not. But it does not allow you to actually get the data of the problem and manipulate it in any way you like. So it's not a violation. Yeah, so the question was about problems in which there is a high sensitivity to initial data. And all I can say, if I am to answer briefly, is yes, you can model this. You can even model, there are models, computational models that describe what it means to compute with real numbers. Here I didn't mention this, but there are models looking into that and looking into smoothing or the numerical analysis of various problems. And you know, that's a field of study that is worried about these issues. Yes.
There are some urgent questions. We should think of the reception. I remind you all that you're invited to reception in Fold Hall. The way is easy to find. And I would like to thank the speaker once again. We could all thank the speaker for a